Good morning, Multi. How are you? And good morning, Mrs. Green, who is, I think, with you guys right now. And I think the best thing for you all to do is to put your headphones in for the screencast. But first, what I want you to do is go over the homework that you had. There may be some questions. That homework was on partial derivatives, and I think it was also some limits too. If you wouldn't mind, just take a second to consult with each other. And then anything that you can't resolve, I'll make sure I do so when I see you tomorrow, okay? Now, for this screencast, what you're going to want to do is I'll be pausing intermittently, and you want to make sure you take notes as if we were in class together. And hopefully, if I'm seamless enough with this screencast, we shouldn't skip a beat. Bailey, I know you are set to meet today for third period extra help, but unfortunately, I am not going to be in today because I am home with a sick child. All right, so now you've gone over homework and you've kind of talked that out. Here's a question for you. And like I've said several times, in multivariable calculus, one of the things that you'll notice is that the actual math, like the computation and the algorithms that you work through, those are actually very easy. It's making sure you understand what the math means that's the part that's a little bit more tricky and more difficult. Okay. So here's your first question. I gave you a function here, and I wrote that you intend to use the appropriate tangent line at 3, 2. So here is the xy ordered pair that corresponds to the point of tangency. And you intend to use the appropriate tangent line to approximate f of 3, 2.2. Will your approximation be an over or an under approximation? I do want you to use calculus here. Obviously, I don't want you just to plug in 3, 2 into z and then plug 3, 2.2 into z and compare those two values. I actually do want you to use calculus. So go ahead and think about this, maybe talk about this, and if you need a mini hint, then replay me. So pause me for now. Okay, here's the mini hint. The key here is figuring out what is the appropriate tangent line, because when you're talking about 3 dimensions and you have a surface, at any point x naught, y naught, comma z naught, there are infinite tangent lines, correct? Because those tangent lines can kind of spin around 360 degrees at that point on the surface. So the hint here is to figure out the appropriate tangent line. Let's think about the point of tangency and the point at which I want you to approximate. And you'll notice that when I go from 3, 2 to 3, 2.2, x is being held constant. So what's changing here is the y value. And so the appropriate tangent line, this phrase here is key. The appropriate tangent line here is going to be in the y direction. And if we're thinking about this surface, we want the line tangent to z at the point 3, 2, f of 3, 2 in the direction of the y-axis, or in the direction of, parallel to the y-axis, so to speak. Because if you notice here, I'm changing from the point of tangency to the point in question. I'm only changing in the y direction. So the critical computations here are looking at dz by dy, okay, dz by dy, and this here would give you, if I asked you to find the equation of the tangent line, actually let's add that piece just to make sure that we kind of shake off the Monday morning groggies. Find the appropriate tangent line, okay, the equation of the appropriate tangent line, and then determine whether your approximation will be over or under. So when we go about doing this math here, the critical computation is dz by dy at that point 3, 2, okay? This is going to equal the slope. That's the slope of the tangent line. Now, here's what's so very important. When you figure out the point of tangency, the point of tan is 3, 2, let's see, this is 2754, so 108 plus the natural log of 6, right? okay? The X, Y, and Z coordinates. And if you have a calculator, you can go ahead and get the approximation for that number. What's really important is when we have this slope, and remember, we're traveling in the Y direction, right? If I ask you, what is the point of tangency? What would the point of tangency, I'm sorry, let me rephrase that. If I ask you, when I go ahead and kind of plop my values in to this equation of the tangent line, right? This is, of course, I'm in Y and X. What is standing in place for Y, Y1, and X, X1 if we are changing Z as a function of Y? If Z is changing with every Y and X is being held constant? Really think about this. Well, we know the slope is whatever this value is, okay? dz by dy at 3, 2. This number here, whatever that number is, and I trust you can find that. We know that is the slope. But what's going in here for kind of what is traditionally referred to as x minus x1 and y minus y1? Well, the equation of the tangent line is actually z minus z1 equals m times y minus y1. Because in the equation of the tangent line, z is changing as a function of y. X is playing no role in this, okay? So when we go ahead and find the equation of the tangent line, that equation is going to be z minus whatever that value is, 108 plus ln 6 equals whatever you plugged and chugged this to be, okay, times the quantity y minus 2. That's the equation of the tangent line. Really important, really, really important to know kind of what variable is changing, what variable is constant, and then what stands for what in the relevant tangent line. Now, will your approximation be an over and under approximation? Well, we know from last year's calculus that concavity is what tells us about over or under approximation. And the concavity we need to determine is the concavity of z in the y direction. So is this, whoops, I just got a righto. Okay, is the sign of this second partial positive or negative? Like, what is the sign with respect to 0? Is the sign here positive? Is the sign here negative? Does the sign equal 0? So if the sign of this second derivative equaled 0, then it would not be an over or under approximation. It would be an exact value, okay? And you know that if the second derivative is positive, then your tangent line approximation will be an under approximation. And then likewise, if your sign here is negative, then you know that the z as a function of y is concave down. You would have an over approximation. Okay, so a lot going on in this question. Now I'm going to build on it a little bit. I'm going to use the same function and the same point of tangency, but now you intend to approximate f of 3.4, 2.2. Will your approximation be over or under? Okay, go ahead and talk this out. When you feel either stumped or you want a mini hint, replay me. And I should say too, you know, I realized in this previous problem, once I started with the mini hint, I kind of kept going. I didn't really pause again. When I give that mini hint, you know, make sure you pause me if you feel like you kind of have enough nuggets to chew on to pursue you further. Okay, so go ahead and talk that out. And then when you find that you need a hint, ask me. Okay, here's the hint. So interestingly, we're going from the point 3, 2, okay, because the point of tan is 3, 2. Point of tan is 3, 2, comma, and what was the y? I can't find the z. 108 plus ln 6. 108 plus ln 6. Okay, that's still my point of tan. And now we notice that I want to approximate the surface if I travel right 4 and up 2. Okay, and my guess, if I were in a gambling mood, is that many of you went ahead and found this sign and this sign. Okay, and I'm going to go over here and actually find those signs in a minute. You probably went ahead and found these two signs to determine the concavity of z in the positive x direction and the concavity of z in the positive y direction, because you notice that we are heading right and up. Okay, let me go ahead and find those second derivatives and I'll replay myself. Okay, so here over to the side, what I did was I took the relevant first and second derivatives and then evaluated both those at the point of tangency. And I just realized I just lost like a little d squared z by dy squared and d squared z. Okay, right there. And I found the appropriate derivatives. And what I have here is that the surface is concave up in the x direction, concave down in the y direction. And if I were a gambling woman, I'm guessing that you all said, well, based on these two results, I would say I can't tell, right? It's inconclusive. I don't have enough information. And I would say to you, nope, that's not correct. You absolutely can tell. And I guess my other question to you is this. Even if they had both been the same signs, let's just play with this idea. Let's say that we found that this second derivative was positive and we found that this second derivative was positive if. Would we then be correct in concluding that the approximation from 3 to, the approximation at 3.4, 2.2 would also be an over approximation? The answer is no. You would not be correct in saying that. So my answer to the question here is, for the question here, whether these signs were the same or they were different, this information alone does not give you enough information to determine whether the answer to this question for the approximation at 3.4, 2.2 is an under or over approximation. So yes, you can't tell. But the reason you can't tell is not because they are different. You also can't tell if they were the same. And I'll show you a picture of that in a second. Actually, I'll show it to you right now. Take a look at this, for example. If you look at this surface right here, and I'm not saying this surface is what we're looking at, but if you look at this, I'm going to put the origin right here in the middle. If I look at the let's say that the x-axis, positive x-axis here, everyone, can you see that? And the positive y-axis is here. Let's just kind of orient ourselves this way. Do you see how that the second derivative, right, d squared z by dx squared is positive here, and d squared z by dy squared is positive here, but do you see how then it's concave down, kind of in the positive and x and y direction, like at 45 degrees from the x and y axis? So this figure, in case you're curious, is called a hyperbolic paraboloid, in case you want some good dinner conversation, or if you're at a party tonight, you can kind of pull this out of your pocket and take a screenshot, you know, with your telephone right here and just kind of whip it out for some good, you know, conversation over like a grapefruit spritzer or something. But, you know, this figure tells you that looking at the sign of the second derivative in just the axial directions is not enough for you to conclude anything about what's happening between those two axial directions, right? So the question is, what the heck do you do? What do we do? Well, let's go over here and have a conversation. I'm going to say, buckle up, boys and girls, because we are going to be leaving Kansas for sure. We are leaving Kansas now. All right, here are some questions for you. Look what I did here. And again, at any point, I want you to stop me and then take it all the way, take it, you know, proceed on your own. From the point 3, 2 to 3.4, 2.2, I noticed the change in y is 0.2 and the change in x is 0.4. So I have this equation right here. Okay. And if I were to ask you where this equation came from, I think you'd all be very quick to say that the equation here is just the equation of the line from this point to this point, from the point of tangency to the point of approximation. And all I did here was just solve this equation for y. Okay. Now, what does this represent? Look what I'm doing. F of x comma y. I replaced f of x comma y with f of x comma this y. Okay, we have to know what this represents, everyone. In words, what is this? Well, in words, okay, oops, I did the math first. In words, this here would describe, now listen very carefully, this here would describe the curve on the surface z, quote unquote, above this line on the XY plane. You understand? Or in Koji's, to use Koji's analogy, it's the roller coaster track above this line. And all I did here was I just found what f of x comma 1/2 x minus 3 plus 2 was. I just inputted x comma y into the surface z. And I think I just cleaned, here I am. Yeah, I'm just cleaning it up, and here's my finally cleaned version. This here is, right, that describes the curve on f of xy above the line on the xy plane from, and this line is, again, the line that passes through the point of tangency 3.2, 3,2, and the point of approximation 3.42.2. This is the roller coaster track, so to speak. Now that we actually have the curve, right? We're not just looking at we're not just looking at the curve above the x or the y axis. We actually have the curve above the line, that the specific line we want. You know, the specific line from 3,2 to 3.42.2. That specific line is not just, you know, the x or y axis as it was up here. That line is this line, y equals 1/2 x minus 3 plus 2, right? Okay, here's where I am. Now that we have that curve, now the question is, let's find the relevant second derivative sign at x equals 3. And look at my notation here. Look how I changed to non-partial notation. Why did I do that, everyone? Why did I do that? Because when I'm at this point here, right, this line, this is an equation that describes z as a full function of just x. It's not a partial function of x anymore. So this is correct in switching over to just kind of our derivative notation that we knew back in the day. It's, you know, the not partial derivative, it's the kind of the full derivative of z as a function of x. And I want the second derivative of this at x equals 3. And then below, I just kind of find that here is the first deriv. Okay. And already I'm kind of cringing that I kind of tossed in here. What ends up happening is to take a quotient rule, and I think I kind of faded out on you. Yeah, I did. So the first deriv is right here. And then the second deriv, so the second derivative of the original, whoops, sorry, look at my notation. This is the first deriv. So this shouldn't have a second on there. They shouldn't have twos because, yeah, the derivative of the first deriv will be the second deriv. And the derivative of this expression, 12x squared plus 6x plus u, I just kind of faded out. But you know how to use the quotient rule, I know. Okay, use the quotient rule. Use your calcs with this quotient rule, and it's actually not that bad now that I look at it, but go ahead and use the quotient rule, find the general second derivative, and now what I want you to do is evaluate, if you would, evaluate the second derivative of, you know, of this, of x to the 4th plus x cubed plus the natural log of 1/2 x squared plus 1/2 x. If you would please evaluate this at x equals 3. And the question is this second derivative sign positive or negative? That will then tell you whether your approximation would be an over or an under, okay? And I'm just going to let you figure that out. Go ahead and plug and chug. What is the sign here, okay? Is it positive? Is it negative? Or is it equal, right? What is it? And based on that sign, then you will know whether your appropriate tangent line approximation, your relevant tangent line approximation would be an over or an under approximation. Okay. All right. So I hope that was clear. Your homework is posted. Once again, I encourage you to kind of take a picture of this. Actually, if you want, I can show you some things here. It's really neat. Look at all these hyperbolic paraboloids. Here is kind of your Pringle trip. Here is right here. That is a museum that actually is in the shape of a hyperbolic paraboloid. It's hard to tell. There's some really funky. Here's another view of that same rooftop, which is pretty funky. Oh, this is actually a really good view of one right there. That's in the UK, I think, if I remember correctly. That's a subway station. Again, it's just a portion of a hyperbolic paraboloid. See, concave up in the positive y, but then concave down in the x direction, right? Here's a really neat one. Look at that. What is that? Is that like a hyperbolic paraboloid shaped sun? What is this? CAT students launch floating hyperbolic paraboloid. It looks like a raft or something. Okay. Here's a really neat one too. Look at that one. All right. Anyway, so ladies and gentlemen, it was a pleasure, and I'm sorry to miss you all on this bright and, well, not bright, on this kind of dreary, damp, and squishy morning. But I will see you soon tomorrow, and I wish you a very nice day. Goodbye.